Welcome back. So we have yet another example on the same category of problems as what we had in the last example. So look at this. It says the motion of a peg sliding within a rectilinear guide. So this is quite straightforward. It just tells us that already tells us that it's rectilinear motion, and it also gives us how the coordinate is measured. So it's quite straightforward now to tell that this is rectilinear motion, so we don't have to state any assumption or anything now. So it says that the motion of a peg sliding within a rectilinear guide is controlled by an actuator in such a way that the peg's acceleration takes on the form. So this is its acceleration. Now, what if you were not told? Let's say it just told you that such that the motion of the body is defined by this relation. So it's then left for you to figure out that this is acceleration because this is x dot dot. So dot dot simply means second derivative with respect to time. So when you see dot in the context of the problems we are considering here, it implies derivative with respect to time. So dot dot implies second derivative with respect to time, just as x dot would have implied first derivative with respect to time, which is velocity. Okay, so it tells us that the acceleration of the body is of this form. So looking at this, we're told that c is time, a naught is 3.5 meters per second squared, omega is 0.5 rad per second, and beta is 1.5. So from all of this, we already can tell that A naught is a constant. Okay, we can see constant in that it does not vary with time, it doesn't change with it does not depend on any other variable as well, it doesn't vary with time and position, and it does not depend on any other thing that varies with time and position. Okay, so this is um, just 3.5 meters per second squared. That is a constant. This is a constant. This is a constant. So looking at this equation, x is clearly a function of time only because it varies with the time only. So as time changes, sorry, x dot dot is only a function of time. A naught is a constant. Omega is a constant, beta is a constant. So the only variable here is t. So this is acceleration depending on t. Okay, so that is clear now that it is of the same form as the problem we solved in the last lesson. Okay, so this is the detail we already have, and now the question asks that we determine the expressions for the velocity and the position of the peg as functions of time. So we want to get the velocity and position of the peg as function of time. If so, in this case, we've been given the initial conditions. X dot is 0. That's velocity, as is, you might guess. Velocity is 0 when time equals 0, and position is 0 when time t equals 0. So it's similar to what we did in the last lesson where we were asked to find the velocity and position first as a function of time. So that's exactly what we're doing here. And this is the expression we use for our acceleration, knowing the values of these constants already. Okay, we might just put them in directly. We can just insert them directly here, and just so that we just have this acceleration as a function of time. We might also work with this as it is, get our result, then insert all of these values so that we have it directly as a function of time. Okay, and the B part says we should determine the total distance traveled by the peg during the interval from 0 to 5 seconds. If, in this case, the initial position, sorry, the initial velocity, this is x dots at 0, is a naught beta over omega. So let's go ahead and deal with this problem now, having interpreted all the necessary things here. So the solution to this, we have acceleration as a function of time. So we list the things that we have been given. Of course, we know that the motion is being measured, okay, with respect to the x axis, and the direction, the unit here is in meters. Okay, so and the direction of this already given is to the right, it's positive to the right. Okay, so this is just an illustration of the motion of the body. Okay, we may or may not need it. Okay, and if we need it for the second part, we might have to draw another one for it. So let's identify what we have been given and proceed. We have been given x dot dot. So we just identify that acceleration is, of course, x dot dot and that has been given as a naught into 2 cos omega t, a naught into 2 cos omega t, and so 2 cos 2 omega t, please. So this is 2 cos 2 omega t. Then this is minus beta sine omega t. So this is minus beta sine omega t. All right. So where in this case a naught is 3.5 also. So let's write that out as well. We have been given that a naught is 3.5 meters per second squared. We've been also given that omega is 0.5 rad per second. Omega is 0.5 rad per second. And we also know that beta is 1.5. Okay, so it's unitless, it's just 1.5. All right, so with that, we are good to go. Let's now go ahead and solve for the first part that asks that we get x dots as a function of time, okay, which we know it's velocity as a function of time, and it also asks us for position itself as a function of time. So how do we do that? Again, we ask ourselves, this is unknown but required. So how does it relate with the known parameter? So this is acceleration. We know acceleration, we need velocity. So we just say that again, recall that acceleration is equal to derivative of velocity with respect to time. So by that, we substitute this expression for acceleration. We have a naught into 2 cos 2 omega t minus beta sine omega t, and this is equal to the v dt. So again, we integrate this, we separate out the variables. This gives us the v equals a naught into 2 cos 2 omega t minus beta sine omega t, then dt. So we have this as constant. We already know a naught is a constant, so we can integrate this directly. We can leave this out and just integrate this. And of course, we might be interested in putting in the initial conditions directly. So let's have a new page. We can put in the initial conditions. Don't forget that we're given these initial conditions. We're given initial conditions for this problem. We're told that x dot is 0, that's velocity is 0 at time t equals 0, and x is 0 at time t equals 0. Okay, so we have that in mind when dealing with this. So we might say now, because all of these constants are already known, okay, we already have them up there. Okay, so we can just insert this directly. So at time t equal to when velocity is 0, time is 0. This is being integrated with respect to time, so we'll put in initial value of 0, and when velocity is 0. Okay, so it's not that whenever we're doing this, it doesn't mean we always have to put 0 here. Please, we just have to use whatever initial condition we have available. So if this was a situation where we were given, let's say x dot is 20 when time equals 5, that's exactly what we'll have here. It means that we'll put when v equal to 20 when t equal to 5, and then we want to find v at any other time t, okay, at any time t. All right, so that's okay now, because although there are constants here, we don't have to solve for them because they are already given. Okay, so we just avoid the the constant of integration, okay, complicating our issue any further. So let's just go ahead and deal with this now. So the integral with respect to v, okay, of 1, this is just integral of 1 dv, so that's just v. All right, of course, to be evaluated from 0 to v, of course we know that is v. All right, but let's write it out like that. So this is integral, so let's integrate this first. Okay, we're integrating with respect to t, So 2 is a constant. Integral of cos 2 omega t. Integral of course that is sine because we know it's a sine that gives us this. So we'll have this to be 2 sine 2 omega t. Then we know that this is not just cos t, this is cos 2 omega t. So we have to divide by the derivative of this to complete this integration. So we divide by derivative of 2 omega t. So I hope you understand what this is. This is just saying that we have 2 omega t. Okay, so we can say, you can imagine that that is in the bracket. So integral of this will be 2 omega. So sorry, derivative of what we have here, derivative of the core will be 2 omega. So if that looks confusing to you, you can do this integration by saying let u, for instance, be equal to, or let okay, you can't use v here, we already have v to avoid confusion. You can say let h or let any other parameter be equal to 2 omega t, then you simplify this, that will be 2 cos h. So if you do that, you have to change this to t as well. So the t will be the h divided by 2 omega. So that's literally how we came about this 2 omega. So if you can't relate directly with this integration like this, then just do that easily. Okay, following that step by step. Okay. This is not a course on integration. That is why I'm just doing this directly, and suspected that at least you know some of these basic things before now. Okay, but if you don't know, just revise them and just practice that by using the substitution I just spoke about now. Okay, so that is for the integral of this part. Then minus beta is a constant, so let's leave it like that. Integral of sine omega t. Integral of sine is minus cos. Okay, so this is multiplying minus cos omega t. Again, the argument a is omega t, so we need to divide by its derivative with respect to time, which is omega, and then we can close this. So that's everything for this integral. And then we know we need to evaluate it from 0 to t. Okay, so please don't always assume that the zero part is going to give you 0. That was exactly why I did not write it out directly when we solved the last problem. I don't want you to get used to just assuming that, oh, when we put in 0 it's going to give us 0. So that is a common pitfall when you're solving this kind of problem. Now this is not likely to give you 0 when you substitute 0. Okay, so you have to calm down and do the substitution and see for yourself. Please evaluate it carefully. Okay, so this is going to give us v minus 0. So this is v minus 0 equals a naught into, so when we substitute t now, we're going to have a naught into 2, we cancel this 2, so this is going to be 1 over omega multiplied by sine 2 omega t. This is plus, this becomes plus because of minus minus, so this becomes plus beta over omega multiplied by cos omega t. Then we close that, so that's what we get for the t part, and then minus what we do for the 0 part, that will be not what we do for the when we have it for the 0 part, that will be a naught into 1 over omega. Then this will be sine of 2 omega multiplying 0. Okay, 2 omega multiplying 0. Then plus beta over omega multiplying cos. Okay, and then we have omega multiplying 0. Okay, and let's write this properly. And that is all about that part. So what is the next thing now? This is going to be a naught. Of course, we have dealt with this completely, so let's leave it at that. So we can, yeah, we can write these brackets. We can write this as 1 over omega is common to both of them, so we can put omega outside. And this is going to be just sine 2 omega t, then plus beta cos omega t. So that is that for this part. And then for this other part, we see that this is 0. This argument becomes 0. Sine of 0 is 0. So this is the part that gives 0. Okay. This is 0, but cos of 0 is 1. So this is plus omega. This is plus beta over omega. So this is going to be minus a naught over omega multiplying beta. All right. So by that, we have now our velocity. So therefore, velocity as a function of time, if we don't substitute yet the values of these constants, this will give us a naught over omega. So a naught over omega is common to both of them. We can just write this as a naught over omega into, of course, there's no need for this. Let's just maintain that as sine 2 omega t, okay, plus beta cos omega t, then this is minus beta. Okay, so now we'll close the bracket. So with that, we're good to go. We now have our velocity as a function of time. So what do you think we might do next? We might just substitute these values now. Okay, so it's good that we already have this in symbolic form. So if we wanted to get the answer in symbolic form, for instance, if the values of those constants were not given, then our final answer will just be this way. But now we have the values of the constants given, so we should just have them substituted and so that we just find v as a function of time directly. You might be wondering, why didn't we just substitute here, get a directly as function of time so that we don't have to deal with this constant again? Yes, that is okay. You can do it like that, but like I said when we did in last chapter, that it is more appropriate for you to work as far as possible using symbols first before you do a final substitution. Okay, so that's why we are approaching it this way. And just to also let your mind be accustomed to problems where you just need to have the answer in symbolic form. Okay, so it's good to just have yourselves exposed to all of this already, so that if you have to solve that just in symbolic form, then you know exactly what the solution should look like. Okay, but for now we have this already, so we can just make our substitution and get the final results. Okay, as for v as a function of time. So by using the values we already know, we have a naught to be 3.5, omega to be 0.5, and beta to be 1.5. The units take care of themselves already because the given equation is consistent dimensionally. Okay, so we just go ahead to make the substitution now. So we say that v as a function of time, I will substitute all of these value. A naught is 3.5 meters per second squared. Omega is 1.5. Okay, is that correct? Yeah. Rad per second. Rad per second. Rad is dimensionless, so omega is 0.5. Sorry, so this is 0.5 rad per second. So let's correct that. This is 0.5. And then let's have this here. This is going to be sine 2 into omega. Our omega is 0.5, then multiplying t, then plus beta. Beta is 1.5, then cos omega t. So this is omega is again 0.5, 0.5 multiplying t, then minus beta, which is 1.5. All right, so we'll close this bracket. All right, so this is 3.5 over 0.5. That is 3.5 divided by 1 over 2. That is 2 times 3.5, which is 7. So this gives us 7. 2 times 1, 0.5, that's 1. So this is basically 7. If we open up the bracket, that will be 7 sine. You can leave it outside anyways, but just let's open up the bracket. This is going to be 7 sine t. Okay, so this becomes sine t because 2 times 0.5 is 1. So then we have 7 times 1.5. That's a 7 plus half of 7, which is 3.5. So that is 10.5. So this is going to be plus 10.5. Then this will be cos 0.5t. So this is cos 0.5t. And then this will be minus 1.5 times 7 again, that is 10.5. Okay, so that's everything we have here. And of course, this will be in meters per second. So this is our velocity as a function of time. Okay, so if we needed it in symbolic form, this will be the result. And because we're already given, okay, because we're already given the constants, then this is just the best way to have this result. Okay, so let's just ignore this. Yeah, so this is our answer for velocity as a function of time. We can now go ahead and look at the second part of the problem. The second part of the problem says we should get position, okay, of the peg as a function of time, and we are given the initial position to be 0 as well. So let's go ahead and do that. So we can use this directly. We can also use this and get a position as a function of time, so that we have a symbolic result, and then we substitute into the symbolic result and get our expression as a function for position as a function of time. So we say that to obtain x as a function of time, recall that velocity equals the x dt. Okay, so that's all we need. That's the relation we need, because this already but known as a function of time. So by this, we'll have the x, and we'll collect like terms, to be equal to v dt. Yes, of course, we will substitute this velocity now. So this is going to give us, I still want to work with the symbols first. So again, this is to get you exposed to working with symbols. Okay, this is a naught over omega, so this is going to be a naught over omega into sine 2 omega t. So this is sine 2 omega t minus or plus beta cos omega t plus beta cos omega t, then minus beta. All right, so this is minus beta, okay, then dt. All right, so this is v right here, this is dt. Okay, so we can say that we have substituted for this to happen, or for us to arrive at this, we've substituted this equation, say equation star. All right, so it's what we substituted here. Okay, so this follows from equation star. Okay, so with that, we're good to go, and this is going to be integral of these. Of course, both of them are constant, so just you can just ignore that and put the integral right in here. Let's write that integral sign. So we can leave it here anyways. So this is going to be we know the initial conditions. Okay, so we're told that x equals 0 at time t equals 0. Okay, that's x of 0, that's x when t equals to 0 is 0. So we're going to insert those so as to use do a proper integral directly. So this is going to be x, I mean, at time t equals 0, this is with respect to t, x is equal to 0. So what is x at any time t? All right, so this is integral of 1 with respect to x, that is x. We evaluate this from 0 to x. Please get used to writing this out like this. The reason I'm doing this is so that you don't assume that when you're substituting 0, it's always 0, please. Because there will be situations where you don't have 1 dx to integrate. So please just get used to writing it out properly. Before you do the evaluation, please write it out completely first. So this is going to be a naught over omega is a constant, so we can just drag that out and leave it there. Then integral of all of these that we have left, that is, let me use braces here. This is going to be sine of 2 omega t. I'm sorry, integral of sine, that will be minus, of course. So this is minus cos 2 omega t. All right. Then we divide by the derivative of the argument. derivative of this argument is 2 omega. Then we have plus beta is a constant, cos of omega t, integral of cos, that is sine omega t. Then we also divide by derivative of this, which is omega, and then we'll do minus beta. Okay, beta is a constant, so that will be minus beta t. Okay, so we close all of this, and of course we evaluate it from 0 to t. All right, so we're good to go. So let's have an additional page to proceed. We have now to deal with this one. We substitute for x equal to x, that gives us x. One substitute for x equal to 0, that gives us 0. And this gives us a naught over omega. Let's deal with this first to tidy it up. We have omega here, we have omega here, but we don't have omega here, so we can move out this omega. So let's leave it as it is and say this is um, minus, so this is minus 1 over 2 omega, all right, into cos 2 omega t, then plus beta over omega into sine omega t, then minus beta t. So that's what we have. When we substitute t, okay, it remains like that. Then let's substitute 0 and see what that gives us. Minus, when we substitute 0, we have a naught over omega into minus 1 over 2 omega, then cos 2 omega multiplying 0, and then we have plus beta over omega, then sine of omega multiplying 0, then minus beta into 0, then we have this. Yeah, so that's that about that. So we can tidy this up. Even for that, this is going to be x, this is 0, so we can ignore that. This is equal to a naught over omega into minus 1 over 2 omega cos 2 omega t, then plus beta over omega sine omega t, then minus beta t, all right, then minus a naught over omega into, so this is cos 2 omega. We know that is 1. So basically this is minus 1 over 2 omega because this becomes 1. And then this is sine of 0. Sine of 0 is 0. So everything here goes to 0. Then this is beta times 0. Everything here goes to 0. Okay, so basically this is what we have for this part. So now we're good to go. We can tidy this up even for that. This is x equal to this becomes a naught over 2 omega blah blah blah. So a naught, sorry, a naught over omega is common to both of them. So we can have a naught over omega into minus 1 over 2 omega cos 2 omega t, then plus beta over omega sine omega t, then minus beta t, then this has become plus, so this is going to be plus 1 over 2 omega. Okay, so that's all that we have left, 1 over 2 omega. So with this, we are good to go. You might want to simplify further and say this is 1 over 2 omega into cos 2 omega t plus 1 blah blah blah, but that is not necessary. So we have now x as a function of time. So to just tidy this up, even for that, we can just substitute now the values of these constants a naught, omega, and beta. So you recall that right here, A naught is 3.5, omega is 0.5, beta is 1.5. Okay, and of course, if we do this now, we can see that everything here is still being divided by omega. Okay, so if you were to extract the omega from this expression, you could have this to be beta, okay, divided by, or beta multiplying omega. So this is going to be omega t if you were extracting omega from this. Okay, so that's just to tell you the dimensional consistency of this equation because you have omega right here. So if you divide a naught by omega squared, that is going to give you it's going to give you meters, okay, directly, because this is a meters per second squared. If you divide by per second squared, that's going to give you meter, which is what we expect x to be, and this will give you omega multiplying t. Omega is in per second and then when you multiply by t, it's also going to give you that result that you need. This already meters, so this is going to give you per second. Okay, sorry, this is going to give you a dimensionless quantity, so as expected of every other part here also after you have extracted omega. Okay, so now we're good to go. We can just substitute the values. So we can now say that therefore x as a function of time will be equal to a naught, which is 3.5, divided by omega, which is 0.5, into all of this minus 1 over 2 omega, that's 2 into 0.5, then cos 2 omega, 2 into 0.5 multiplying t. All right, so we can do all of this together, then plus, let's write that on the next line, beta over omega, beta over omega, then sine omega t, that is sine 0.5 t, okay, then minus beta t, that's beta into, sorry, beta is 1.5. Why did I leave this here, please? This is meant to be, so let's wipe that off. So this is meant to be beta, beta is 1.5 divided by omega, omega is 0.5, then sine of omega, that is 0.5 multiplying t, then minus beta, which is 1.5 multiplying t, then plus 1 over 2 omega, that's 2 into 0.5. So that is that about that. And from here, we now say that x as a function of time equals 3.5 over 0.5, that is 7. Then we have this to be minus 1 over 2 times 0.5 is 1, minus 1 over 1, that's minus 1. This is 1 as well, so this is going to be minus cos t. Okay, 2 times 0.5 is 1, so this 1 times t, which is t, so this is minus 1, minus 1 times cos t, that's minus cos t. Then we have 0.5, 1.5 over 0.5, that's 2 times 1.5, which is 3, so this is plus 3, okay, sine 0.5, okay, multiplying t, so this is 0.5 t, and then we have minus 1.5, okay, t, then plus, this is 2 times 0.5, which is 1, so this is plus 1, okay. So that is that about that. So we can open up the brackets even for that. So this is going to give us x as a function of time, okay, to be x as a function of time equals minus 7 cos t, then 7 times 3, that's 21, is sine 21 sine 0.5 t, then 7 times 1.5, that is 10.5 minus 10.5 t, then 7 times 1, that is 7, so this is plus 7. So all of this will be in meters. Okay, so we can rearrange this and just write it as, just to have the 7, the positive come first, so we can have this as 7 minus 7 cos t, then plus 21 sine 0.5 t, then minus 10.5 t. Okay, so put all of this here and that will be in meters. So with that, we are good to go. Okay, so that is x as a function of time. This is v as a function of time up here. So we're done with the first part of the problem. So let's move on now to the second part of the problem. It says determine the total distance traveled. Total distance traveled, that's specific, by the peg during the interval from 0 to 5 seconds. Okay, if in this case x dots equals a naught beta over omega. All right, so we want to get total distance traveled. Now we're given a different initial velocity. Initial velocity in this case, as we have seen here, is not 0. You know that the A part, for the A part we solved, initial velocity was 0. So we have to be careful with problems like this. In this case, the initial velocity was 0. here the initial velocity is obviously not zero. So we cannot use the result we obtained here to actually solve this problem, especially the result we obtained for velocity, which of course also carries to the result we obtained for position as a function of time. So this tells us that the total distance traveled by the peg, I want to get the total distance traveled by the peg if initial velocity is this. So this is not zero. So which means that we will need to um, find out what this initial velocity is, then use it to get the velocity as a function of time, then use it to find out if there is any turning point. We have to get total distance. So we need to find out if there is any turning point within this interval from 0 to 5. And once we have that established, then we know how to get the total distance traveled. And for that case also, we need to find out what the final position is, okay? So what the position is as a function of time before we can use that to evaluate the position at different times, at t equal to 0, at t equal to this and all of that, okay? So in this case, we go ahead to say that in this case we are given the initial velocity to be a naught beta over omega. So let's evaluate that first. So let's have an additional page. So for the second part of the problem, that is the B part of the problem, we are given in this case that v at 0, okay, that's x dot at 0, is a naught multiplying beta over omega. So we know that implies 3.5. A naught is 3.5, beta is 1.5, omega is 0.5. So this is 3.5 over 0.5, that's 7. 7 times 1.5, that is 10.5, okay, meters per second, okay. So we have the initial velocity to be 10.5 meters per second, all right. So we can get our acceleration as a function of time. We need to start afresh now because we don't know, we don't have, we don't have the same initial velocity as what we used to obtain this result. We cannot use this result, okay, as it is currently. So let's go ahead and see when we substitute. Now we're going to substitute into this expression and get our acceleration as a function of time. So this is acceleration. We don't have to do symbolic approach here because we're not really interested in velocity as a function of time. We need to evaluate distance. Okay, so let's get as fast as possible to our final expression. Okay, so the acceleration is given by a naught into 2 cos 2 omega t minus beta sine omega t. So we will just use that directly. So we're given also that acceleration is equal to a naught, so that is 3.5, okay, into that's 2 cos 2 omega t, 2 into omega, that's 0.5 multiplying t minus beta. Beta is 1.5, then multiplying sine omega t, that's sine 0.5, okay, multiplying t, okay. So this is our acceleration as provided for in the problem. It says 2 cos 2 omega t minus beta sine omega t, okay. Then we have a naught outside. Yep. So this is the expression for acceleration. So let's tidy that up. That's going to give us 3.5 times 2, that is 7. So this is 7 cos 2 times 0.5, that's 7 cos t. Then this is going to be minus 1.5. So this is 3.5 times 1.5. 3.5 times 1.5, so that is 1.75 plus this. I think that is 4.25. I'm not sure of that, so we check that with our calculator. Sine 0.5, so this is sine 0.5 t. Okay, so that should be 5.25 or something. Let's bring up the calculator. So this is 3.5 times 1.5, 3.5 times 1.5. Okay, so that is half of 7 times 1.5. That is 5.25. Sorry, 5.25, not 4.25. Okay, so this is 5.25. Yep. So this is 3.5 times 2 is 7 cos t, then 3.5 times 1.5, that's 5.25 sine 0.5 t, right? So we're good to go right here. Yep, good to go here. So if we want to get the velocity as a function of time, now it's we have a different initial velocity to deal with. So let's go ahead and say that we know that A is equal to the V dt, which means that A dt is equal to the V, okay, by cross multiplying, of course. So which means in this case, our dv is equal to A. Our A is 7 cos t minus 5.25 sine 0.5 t, okay, then multiplying the t, and then we can integrate this and integrate this so that we have velocity as a function of time that applies to this situation. Okay, so in this case, we have our initial velocity to be 10.5. So that means that at time t equals to 0, this was 10.5. So we want to find out what v is at any time t. So by this, we go ahead to evaluate this. This becomes v, okay, integral of 1 with respect to v, that is v. So this will be evaluated from 10.5 to v, and this is equal to integral of 7 cos t, that is just 7 sine t, and then integral of this integral of sine is minus cos. So with the minus here, this becomes plus. This is 5.25 cos 0.5 t. This is cos 0.5 t. Now we divide by the derivative of this argument, which is 0.5, and then that's everything about this integral here. We know that we need to evaluate this, okay, altogether from 0, okay, to t. So let's find out what that gives us. That's going to give us v minus, when we substitute 10.5, that is 10.5. So that is not 0. It's essential to write that out. So this is going to be, when we substitute t, is going to remain as t. So this is going to be 7 sine t. Then this is going to be 5.25 times 2. That will be 10.5. So this is going to be plus 10.5 cos 0.5 t, and that's all for the t part. And when we substitute 0, this gives us 7 sine 0 plus 10.5 cos 0.5 multiplying 0, and we close the bracket. All right, so with this, we now say that this gives us v minus 10.5 equals 7 sine t. So this is 7 sine t plus 10.5 cos 0.5 t, and then this is going to be sine of 0 is 0. Okay, so cos of 0 is 1, so this is 10.5, so this is minus 10.5. All right, so with this, we are good to go. We know this carries minus 10.5, this carries minus 10.5 as well, so this will chop this, and by that, we'll have v to be equal to 7 sine t plus 10.5 cos 0.5 t. So is it different from what we had before for v? So you can see that yes, in this case it does not carry this 10.5, okay, because it has um cancelled out. Okay, so that is that about that. We have the initial velocity to be 0, okay, and that would have given us some advantage here. If we actually would have had some advantage here if we did not evaluate this from zero directly, I mean, if we just integrated and introduced the constant of integration and kept the result, we would have just used it here so that for this different initial condition, we evaluate a different constant of integration and just move on with that. Okay. But anyway, we have the results that we need. So um, we can now go ahead and see when will this be equal to zero. That is, we know we need to find the total distance traveled. If we're going to get the total distance traveled, we need to evaluate, we need to find out if there is a turning point in the interval of interest. So if there's a turning point within that interval of interest, then we know that we have to find out the distance the body has traveled from zero to that point, then from that point back to when time t was 5, and then we put up those, so we add, we sum up all of those distances to get the total distance traveled. Okay, so the challenge before us is to evaluate what happens when v, that is the velocity of this body, is equal to zero. So when we evaluate that, that is, we want to find out the time at which the velocity is equal to zero. Okay, so we say that to find the turning points of motion of the body, okay, we set v to zero. Okay, so therefore we have zero to be equal to 7 sine t plus 10.5 cos 0.5. So we need to find out by solving this equation what will be the time at which the velocity is zero. That will give us the turning point of the body. Why is that necessary? That's always necessary when we need to find the total distance traveled, so that we know if there's a turning point within that interval first before we begin to put up all of the distances. Because as we defined, distance traveled by the body is the total length of the path followed by the body. So we need to know if it's moved toward, got to a particular point and turned back. So we need to capture all of those things. That is why we are having to deal with this equation now. So now this is quite an interesting problem because the arguments to our trigonometric functions here are not the same. The argument here is t, the argument here is 0.5 t. So we can ask ourselves, how do we make the arguments become the same? So this is half angle. This is like we have 1 over 2t and we have t. So we can make the half angle become t so that we will relate them and see when this equation will be satisfied. Okay. We can also consult our calculator to see if our calculator can solve this directly. Good luck to us. That makes it extremely easy to deal with, and if it gives us the time at which t is 0. Okay, we know that this can give us several results. Okay, so basically we might want to ask ourselves, okay, if we find out from our calculator the solution to this equation, will it tell us all the possible solutions? That's quite unlikely. Then that means we are likely to fall into the error of assuming that there is no solution in the interval from 0 to 5. Okay, so let's see firstly what the calculator says about this. So we enter the function in our calculator and equate it and solve for it when t is when everything is equal to 0. So 7 sine t, I'm going to use here x instead of t, so it doesn't matter. So this is 7 sine alpha x, so close the bracket, plus 10.5, so this is 10.5 cos 10.5 cos 0.5 t, that's 0.5x, then we'll close the bracket. So we can evaluate this. If we want to calculate for this at different values of t, we can just press the calc button, but we want to solve when the entire equation is equal to some expression 0 now. So we can still solve up there. It's the second function of this calc. So we can press shift to access that second function and then press calc. So we solve for x when this is equal to 0. That is when the entire expression is equal to 0. So it tells us that x is equal to minus 1.69. Of course, our calculator is in radian, so this result is in radian. Okay, the result it just gave us now. So it tells us that this equation has a solution at minus 1.6962 blah 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 radians. Of course, that minus is not within our interval from 0 to 5. But this is tricky because this is not some algebraic expression that we can easily tell, okay, this is quadratic, this is um, cubic, and so on and so forth. And so we can easily tell this the solution is within a certain interval and all of that. But in this case, this is a, let's say, a sinusoidal function, okay, a trigonometric function which will have its result in cycles. You know what I mean by that? Because for every new cycle, you're going to have a result that lies there. This is a trigonometric function, okay? So this does not capture all the solutions completely. So we cannot rely on these results that gives us one singular result. So another way we can find out if there is a solution within the interval from 0 to 5, because we are really just interested in interval from 0 to 5. Another way we can find out is this. So we know this from our knowledge of calculus that if a solution lies in that interval from 0 to 5, then if we evaluate this function at 0 and then we evaluate it at 5, we might just get them to be opposite values. Okay, now if we get them to be the same value, it does not really tell us any, it doesn't tell us anything. The solution might exist there, and then we don't have the values to have, or we don't have the function to have opposite sides there. This is what I mean by that. If we were to graph this as a function of time now, so if you have this here and we graph this relation as a function of time, for instance, we want to get the solution. That is when this will be equal to 0. So let's say that the behavior is like this. And then what happens at between 0 and 5? Let's say at t equal to 0 now, we see this is here. It is positive. At t equal to 5, let's say it is here. It is also positive. It doesn't give us any information. Even though there are solutions in between, it does not give us any information. But if we're very lucky, if we're using this approach and we're checking and we're very lucky and we find it to be that, let's say at t equal to 0, this thing is here, positive. At t equal to 5, it is here, it is negative, then we know definitely there is a result, there is a solution in between. But if they are both positive, we cannot really tell. It may happen that there's actually a solution like we have it here, and it may happen that there's no solution. Maybe the behavior is just like this, okay? And there's no solution, there's no point where it crosses the line at 0, okay? So that's the point here. But if we check this now, it's just some rough work anyways. If we check for what happens at time t equal to 0 and what happens for the value of this function at time t equal to 5 as well. So we can get back to that and just check. So we want to calculate this. Ensure your calculator is in radians. So this is when t equal to 0. It gives us 10.5, which is 21 over 2, of course, which is the initial velocity that we have up there. And when t equal to 5, for instance, so let's calculate when t is equal to 5, what happens? This has gone to minus 15. So definitely it will become 0 somewhere in between, between t equal to 0 and t equal to 5. That means we are 100% certain that there is a solution between t equal to 0 and t equal to 5. So because for it to go from 10.5 velocity to go from 10.5 to minus 15.1, it has to pass through 0. So where is that point where it was at 0? Between time t equals 0 and t equals to 5. Where did that velocity become 0? That is the work for us to do now. We need to find out where that happens. And that means we don't have an option. We have to come and solve this equation. And now, the best way to solve this equation is to write either this or this so that we have half angle to deal with. Okay, so we can write this as I have an expression for this so that it just carries what is it called now? It just carries t as arguments. Okay, so we need to do a bit of trigonometry here. So we now say that for us to deal with this. Okay, so just recall that, for instance, if you want to deal with what is it called now, cos of which one of them should we change. Let's change this to cos or we'll change this to sine. Which of them will be more effective or efficient for this problem? So let's have this changed. So let's have cos. If you want to do that, of course, you should recall that cos of a plus b, for instance, is cos a cos b. This is one of your trigonometric formulas minus sine a sine b, not beta. This is sine b. And if that is the case, it follows that cos of, let's say, 2 theta, for instance, is that will be cos of theta plus theta. So that's going to be cos theta. That is going to be cos squared theta minus sine squared theta, right? And and if you want to simplify this further, let's say in terms of cos or in terms of sine, then you can say that what we have here is equal to what can we call these? Is it better to have the result, to have a final expression in terms of cos, or have it in terms of sine? Okay, so it is better to have it in terms of cos, and the reason for that is that looking at the quadrant of angles, I want you to understand something. Looking at the quadrant of angles, this is look at this now. If we are starting off with this interval, let's say that we know that from this point to this point we have 90 degrees, and then this to this point this is 180 degrees, and then this is 270 degrees. Okay, so if we are looking at this, for instance, we can see that sine is positive here, sine is also positive here. So if we work with sine, for instance, if we have an answer that is meant to lie here, it's going to be problematic because sine will just capture both of them as positive, okay? But if we use cos, it better captures a longer or a wider range, okay? So it captures a wider range because when it is here, it's going to be positive. When it is here, it's going to be negative. So it better captures the results that we are looking for. Don't forget, we are looking for what happens between 0 and 5. And this is like you have something between angle in terms of the angles. Now, this is 0 to pi over 2. This is 0 to pi. Don't forget, pi is 3.14 something, blah, blah, blah already. So that better captures it. And of course, if it is from this point to this point, we know that is between pi and pi plus pi over 2, which is 3 pi over 2, okay? Or say 3 pi over 4, right? So that is the, 3 pi over 2 actually. So that is going to capture the results better. So it's good if we have our final expression in terms of cos instead of having it in terms of sine, okay? So guided by that, we can just write this as cos squared theta, okay, minus, we know that sine squared theta is 1 minus cos squared theta. So we can use that to simplify this from the fact that sine squared theta plus cos squared theta equals 1. So this is one of the trigonometric relations you know by now, or you're expected to have known. So by this, we will have this to be cos squared theta minus 1, then this becomes plus, okay, cos squared theta. So this is going to give us cos squared theta plus cos squared theta, that is 2 cos squared theta minus 1. And now this tells us that we have cos 2 theta to be equal to this. So this gives us a relation between cos 2 theta and cos theta. Okay. So what we need to know, what we need to do is we need to replace this expression here that as this is theta over 2 or t over 2. So look at it now. If we have if we have t over 2, 2 times t over 2, so it will follow then that cos of 2 multiplied by 1 over 2t. I hope you understand that because we have 2 here multiplied by theta. So we're replacing theta now by 1 over 2t. that will be equal to 2 cos squared theta. Our theta is 1 over 2t, and then this will be minus 1. Okay, so simplifying this further, we know that this is going to be cos 2 times 1 over 2, that is 1. So this is cos t equal to 2 cos squared 1 over 2t, that's 0.5t, then minus 1. So we want to replace this now. We want to replace this expression here that has cos 0.5t. We want to replace it by cos t. So we can just make it the subject from here. So we're going to have, when we bring this to the other side, 1 plus cos t is equal to 2 cos squared this. So when we divide this by 2, we're going to have cos squared 0.5t, and from here we'll have cos 0.5t to be equal to, so all of this 1 plus cos t divided by 2 to the power of 1 over 2. All right, so that's when we take the square root of both sides. So we have this expression now. That's a lot, but we just put it here. Okay, so this is an extreme problem anyways. So but it's good that you are exposed to extreme cases like this so you know how to deal with it. Okay, so now we just substitute this expression, okay, for cos 0.5t in this equation. Okay, so let's say this is equation star star, for instance. We just put that up there once we're done with this. So it then follows that in equation star star we'll have 0 to be equal to, okay, from equation star star now, having found an expression for this is 7 sine t, so this is going to give us 7 sine t, then minus or plus 10.5 into, this will be plus 10.5 into this expression, so this will be equal to 1 plus cos t to the power all over 2 to the power of 1 over 2. Okay, so that is that about that. We now have an equation where the trigonometric functions present have the same arguments. So that's the purpose of what we've done so far. Okay, so we now have to deal with this. Of course, we can simplify this even further by recognizing that sine t itself is, from what we did, from what we observed here, that's sine squared theta plus cos squared theta is 1. We can get an expression for sine t as well. When we make sine theta the square, that will be square root of 1 minus cos squared t. So by that, when we separate this out, we're going to have this to be minus 7 into the root of 1 minus cos squared t, okay, all to the power of 1 over 2. Hope you understood what I just did. I just moved this to the other side. So that's what brought about the negative sign. And instead of sine t, we have square root of 1 minus cos squared t. Okay, from the fact that we're going to have, we have sine squared t, okay, plus cos squared t to be equal to 1. So which means that sine squared t will be equal to 1 minus cos squared t. And if we solve that for sine t, that will be square root of 1 minus cos squared t. So that's exactly what we have written here. Instead of square root, we wrote to the power of 1 over 2. So which implies the same thing from knowledge of indices and powers and all of that. So we are done with that part. Then we'll have this to be 10.5. 10.5 is 21 over 2. I mean, I just want to have something to cancel on both sides. So this is going to be 1 plus cos t divided by 2, then to the power of 1 over 2. Then to clear off these powers, we can just square both sides. Of course, before we do that, this is 1 and this is 3, so this is basically 3 over 2. Then when we square both sides, this is minus 1, this becomes positive, and then this gives us 1 minus cos squared t equals, when we square this is going to be 9 divided by 4, And then when we square this, that gets rid of the square root sign. So this is going to be 1 plus cos t divided by 2. All right, so now we're good to go. We have an expression now, of course, quadratic, in terms of t, in terms of cos t. So we have only cos t present now. So, why we were driving towards this path, okay, or towards this destination. Now, also, we have this to be 9 over 8. We can open up this bracket and say this is 1 minus cos squared t equals 9 over 8. Okay, 9 over 8 times 1, that's 9 over 8, then plus 9 over 8 multiplying cos t. Okay, so by that, we can rearrange this so that we just form a proper quadratic equation. So when we move this to the other side, this is going to become cos squared t. Cos squared t, don't forget, is the same as cos t squared. And then what else do we have? Plus 9 over 8 cos t. So this is 9 over 8 into cos t. Then we have minus 1. We'll move this one to the other side. So this 9 over 8 minus 1. So that is 9 over 8 is 1 over 1 over 8. So basically this is what we have was 1 over 8 left. And then we have this equal to 0. So this is now a quadratic equation in terms of cos t. And then we can just use our calculator to sort that to see what cos t will give us. So let's bring up our calculator and solve this quadratic equation. So assume that what you have inside here, for instance, you can say let p be equal to this and then solve for p, then come back to say p is equal to cos t and solve for that, okay? But we're not going through all of those processes here. We just want to solve this directly. Let's solve for the quadratic equation first. Let's put this equation. The quadratic form is in number 3, and the coefficient of the quadratic term is 1. The other one is 9 over 8, so we'll put 9 divided by 8, and then the last one is 1 over 8, that's 1 divided by 8. And so this gives us x equals minus 1 over 8 and x equals to minus 1. Minus 1 over 8 and minus 1. So, therefore, our cos t is equal to minus 1 over 8, or cos t is equal to minus 1. So life is as easy as that. And now we can solve for, you see why we had to go through this now. We know that cos is negative. So cos being negative already takes our attention completely away from the first quadrant. So we know that the next target will be second or third quadrant. But if we had gotten this result in terms of sign, it will, if for instance the answer is going to lie in the second quadrant, sign will still be positive. And then when we do the sign inverse, it's most likely going to give us an expression that is in the first quadrant, and then we'll begin to um rack our brain and say, oh, what should this be? Let's consider how the how the what is it now, how the argument changes, how it goes from one cycle to another. Let's add 180 degrees to it. Let's check if we add 2 pi to it, what is going to happen and all of that. So that's a lot of problems. So it's better to just have it in terms of course it captures it better. Okay, so this already takes our attention completely away from the first quadrant, because we know that if it were in the first quadrant, cos will be positive. It also completely takes our attention away from the fourth quadrant, but we know that there could be an answer in the second or third quadrants. Okay, so let's go ahead and find out what this would be. And for that purpose, we have to get the cos inverse of minus 1 over 8. So ensure that your calculator is in radian, otherwise you'll be getting a wrong result. Radian is the dimensionless quantity that you use whenever you are dealing with angles. Now, you might be wondering, why should we use radian? Anytime you have to deal with angles and it is not explicitly in degrees, it is radian. When I say cos 1, if I say, okay, find out what cos 1 is without specifying whether it is in degree or radian or whatever, you know already that it is in radian. So radian is that dimensionless quantity. That is one. Another thing is that looking at the parameters given, it's only radian that you should have. You can see this is 0.5 rad per second. So that already tells you that the argument you are dealing with is in radian. Okay, so your calculator has to be in radian while working with this or solving this particular problem all through. You have to be conscious of whatever units of angular measure is required. Okay, so moving further, we will say what is the cos inverse of this. So let's get back to our normal mode. So let's find out what the cos inverse of this is. Cos inverse of 1 over 8. So 1 over 8, that gives us 1.44548 blah blah blah. Sorry, minus 1 over 8 is what we need, please. So this is meant to be minus 1 over 8. It gives us 1.6961 24 and so on and so forth. This is in radians. So let's take note of that. This tells us that T is 1.69, what else? 6961, 1.6961. Okay, that will be in seconds, of course. And then the second part tells us cos inverse of minus 1. Let's check that. Cos inverse of minus 1. So this is minus 1 and it is pi. So this is equal to pi, of course, in seconds. Okay, we know pi is 3.141 blah blah blah. So that's within our interval from 0 to 5. So both of them are welcome. Now there is one last thing to do, and it is to check which of them actually satisfy the equation we started with. Now, why do we have to check in this situation? Because working with trigonometric functions is very tricky in that now along the way we decided to square both sides. We squared both sides here, and we by that we lost track of this negative sign. Okay, which means that by what we have done here, we would obtain some results which will only apply if this was negative. If this was negative, I will move this here, it will be positive, and when we square it, it will still give us the same results. So that is something you have to bear in mind here, that having squared this, we will be introducing something that does not really satisfy what we started out with, but only satisfies the other parts of it where this thing is negative. So that is why we need to check which of the two actually satisfies the equation we started out with before we can finalize on what our result is meant to be. And this is particularly important because in this case, both of them actually happen to lie in the interval of interest. They lie between 0 and 5. So we cannot just even just throw them off. So we have to be careful about what we are doing here. So let's get back to our function and check for what is really going to be or what should be our solution here. So again, this is our expression. So let's evaluate this at each of the values we obtain and see which of them will actually give us 0. Okay. So let's bring up our calculator and enter this function again. 7 sine alpha, we're using x, okay, plus 10.5, this is plus 10.5 cos 0.5x, that is cos 0.5 alpha x, then close the bracket. Let's calculate what happens at each of these values that we have just obtained. So we have 1.6961, so this is 1.6961. So that is not 13, but that obviously is not 0. Okay, so this is a radian, so this is not 0. That means this is not a solution. Okay, we'll come back to see how this came about. Okay, so let's check for pi. So calculate for when this is pi. Where is pi? Right here. So it is 0. So that's just tells us that our answer is pi. Okay, but like I said earlier, the reason we are getting the second answer is because of that square. It will not make a difference when even we have negative here. For instance, if we had negative here and we calculated for this will be 1.6961, and then it will give us 0. This is approximately 0. Approximated because we approximated here. We just pick the first four decimal places here. So this is 0. You can see 10 to the power minus 5, that's 0.000007. Okay, so this solution will apply to when the sign here is negative. Because if the sign there was negative, we would have the same thing here, but it won't carry minus. And when we square it, we still obtain the same expression. So it is the squaring here that introduced the second answer that we obtained here. So, but this answer does not apply to our original equation. So I believe we get the point now. So we now say that, okay, on verifying, we will now say that but, okay, V, okay, at 1.6961, okay, is not equal to 0. Okay, so because of that, we now say that thus our t equal to pi seconds is the turning point required. Is the turning point in the interval 0 seconds to 5 seconds. So this is the turning point that we are interested in. We now have it. That's a lot of work, but we have gotten to our destination. So I believe now you can get the total distance traveled. For us to know that, we just find out the distance between time t equals 0 and time t equals what is that now? Time t between time t equal to 0 and time t equal to pi seconds. Then from time t equal to pi to time t equal to 5, we find out what the positions are. That will help us get the distances. And with that, we are good to go. So we need to find out what position is as a function of time. And for us to do that, we will use this expression that we got for velocity. We will have to integrate this now. So in this case, we need to make use of this position as a function of time. So let's say that was equation, let's say it is equation A. So why are we using this? Because here, for the same reason we found this again. Okay, what was the reason? Because we have a different initial velocity given. Okay, that was why, because we had a different initial velocity given, was why we started over again here. So it is the same reason, it is for the same reason that we have to find our position now differently. Okay, because it will not be given by the same expression as what we have up here. Okay, what we obtained initially. So we will go ahead now and make use of this expression that we have a velocity here. We use it to get the position as a function of time. Okay, so we now obtain, so we now say that to obtain position as a function of time, recall again that v is equal to the x dt. So if v is the x dt, then it follows that v dt is equal to the x. And we can now substitute equation A up there. Equation A provided that our velocity was 7 sine t plus 10.5 cos 0.5 t. So 7 sine t. So provided that we have 7 sine t plus 10.5 cos 0.5 t. Okay, then we take all of these, okay, dt, and say this is equal to the x. Okay, so for this second case, we were not provided with any initial position. Okay, they didn't tell us what the initial position of this body is for this case. However, we're not really interested in the initial position, and that's actually to say that whatever the initial position is will not matter to this problem. Why is that? Because we are interested in distance traveled, and distance traveled simply means how far from the initial position. That means it is the differences that we're interested in. Differences that we're interested in. For instance, if at time t equals to 0, the body is here, and after pi seconds it has gone this far. Okay, that difference will be the same thing even if the body was initially here. So if the body was initially here, for instance, and after 10 seconds it has covered that distance, it will just mean that the final position will be here, but that difference will still be the same. Okay, that distance between the 2 points. So you see what we're talking about as we proceed right now with this analysis. Okay, so let's go ahead and solve the problem completely. So we don't have an initial position for this second part, and we cannot deduce from the problem statement whether it is the same thing as the initial position for the A part. Okay, so we don't know what the initial position is. So to just save ourselves the stress of making some guess unnecessarily, we can say that okay, we want to make the x the subject. This should have the x as the subject, but it doesn't matter anyways. So let's say that we want to integrate this and we want to integrate this. So let's say that the position at time t equal to 0 is x naught. So we don't know what it is. We don't want to assume it's 0. But I promise you, even if you assume it's 0, you'll get the same result. But I just want to leave it here so that you see that it eventually cancels itself out. So let's say that at time t equal to 0, let's say you can notice that this is with respect to time. So at time t equal to 0, let's say the position is x sub 0. Then we want to get the position x at some arbitrary time t. So let's go ahead and just solve for this. Integral of 1 with respect to x, that is x. So we take this from x naught to x, and this is equal to, when we integrate 7 sine t, that gives us minus 7 cos t, and when we integrate this cos, that will give us sine, so this is going to be plus 10.5 sine 0.5 t, and then we can close this bracket and then evaluate this from 0 to t. All right, so that is that about that. Of course, we need to divide by 0.5 here because of the argument here. The derivative of the argument is 0.5. Okay, so that is that for now. And then going further, we will have this to be x. Okay, this is x minus x naught. So this is going to be x minus x naught equals, so this is going to be when we substitute t here, that's just going to give us minus 7 cos t, and then 10.5 over 0.5, that's 10.5 times 2, that is 21. So this is going to be plus 21 sine 0.5 t, and then we have this thing here to just close up, then minus when t is 0, so this is going to give us minus 7 cos 0 plus 21 sine 0.5 times 0, so this is times 0, and we'll close that there. And from here we see that x minus x naught equals, so this is 7 minus 7 cos minus 7 cos t plus 21 sine 0.5 t. I've let go of the bracket, so this is 7 cos 0, which is 1. 21 sine, this is 0, so everything here is 0, so this is minus 7, this is minus of minus 7, that will be plus 7. Okay, so that essentially tells us that x minus x naught is equal to this is going to be 7 minus 7 cos t plus 21 sine 0.5 t. And if we bring this to the other side, this means x at any time t will be equal to, I'll put this here, 7 minus 7 cos t plus 21 sine 0.5 t and plus x naught. So that's a lot. So we just moved this here. So if we compare this with what we had previously, we'll notice some differences there. What we had here was 7 minus 7 cos t plus 21 times 0.5 t, and here we had minus 10.5 t. That was carried over from the fact that the v here had 10.5, but our new v does not have that. Okay, and here our x naught was 0, so it did not have x naught as well. So the other parts remain the same, 7 minus 7 cos t then plus 21 sine 0.5t. Okay, but this part is not present because 10.5 is not present in our new p, and that is that about that. Okay, so let's go ahead and have an additional page now. So that is the idea. That's our position as a function of time. So we can now get the position at x equal to 0. We know our points of interest now. We know we're going from 0 times t equal to 0 to times t equal to 5 according to the question. We have found a turning point at t equal to pi. So that means we need to get the position at x equal to 0, position at x equal to pi, at the position at position x when t is equal to 0, position when t equal to pi, and position when t equal to 5. That would help us see the distances the body has traveled, okay, and then we sum them up to get the total distance we traveled. All right, so we now say that therefore x at time t equal to 0, because of course when we put 0 here, this will be 7 minus 7. Of course we expect that to just be x naught. I mean, that was the assumption we made to arrive at this. Then x at t equal to pi, that will be equal to 7 minus 7 cos pi plus 21 sine pi over 2. I mean 0.5 pi, that's pi over 2, then plus x naught. So that will be equal to cos pi. So what is cos pi? That should be minus 1. Sine pi over 2, that's a sine 90, which is 1, okay? So let's check for cos pi. We got that earlier anyways, but just for confirmation is minus 1. So this will be 7 plus 7, okay? Then sine pi over 2, that's a sine 90. So you can verify that sine pi shift pi, then divided by 2, then cover this, and this gives us 1, okay? So we're good to go. This is 7, okay, plus 7, because this is multiplying 1. Okay, so we can just add them up anyway. 7 plus 7 plus 21, so that is 35 or thereabouts. So this is 7 plus 7 plus 21, so that is 35. Yeah, so this is basically giving us 35, okay, when x is equal to pi. So this is 35 plus x naught, okay, so that is our x when c is pi, and then we get our x when c is equal to 5. So don't forget your calculator has to be in radians, please. So this is going to be 7 minus 7 cos 5, okay, plus 21 sine 5 over 2, that is 2.5, then plus x naught. So this is going to give us x at 5 to be equal to, so let's evaluate this, 7 minus 7 cos 5, so it's in radians, please make sure it's in radians, plus 21 sine 2.5, sine 2.5. So what does that give us? 21 sine 2.5. So this is 17.5822. So let's say 17.5823. So 17.5823. So this is 17.5823, then plus x naught. Yep. So with this, we are good to go. So for illustration of what is really going on right here, we can see that our this is x, okay, which is in meters. So at x naught, so let's say initially the body was at x naught, and then it went to, at pi, it has gotten to 35 plus x naught, that is, it went 35 to the right of x naught, and then by 5, it's got to 17 points. That means it turned back to, for the position to have decreased this way as expected. So let's say this is our x naught, whatever you take that to be now. Then it went to 35 plus x naught, so that will be to this side. So let's say this distance is, this is x naught plus 35, and then at time t equal to 5, it was 17 point something. So 17 point something will be somewhere in between here. So let's say this is x naught plus 17.5823. All right. So This was the position at time t equals 0. This was the position at time t equals 5 seconds. And this was the position at time t equals to pi seconds. So we can now see that the body starts from here at time t equals to 0, then goes this way. Okay, and on getting to this point, it turns back and gets here at time t equals to 5. So these are the distances of interest, S1 and S2. So that's the point. The body goes this way, gets here, the velocity becomes 0, and then the velocity continues to decrease, becoming negative, and then it turns back and then it gets here. So what do we need to do now? We need to find out what is S1, then add it to S2. So that is the idea. So we can now say that hence total distance traveled. I told you that this illustration is required, or you do some graph, or you do both of them. Now, the graph will be somehow here because this combines sine and cos, so we don't really know what the sketch should look like. So, but it's fine to just use this illustration. At least we can visualize what is really going on here. So, hence, total distance traveled. Okay, D equals S1 plus S2. So that will be equal to the modulus of x, okay, at 0. This is x at 0 minus x at pi plus the modulus of x at pi minus x at 5. Okay. So this is going to give us x at 0, that is x naught, minus x at pi. X at pi is x naught plus 35. Then take the modulus plus x at pi again, that is x naught plus 35. Okay. Then minus x at 5. X at 5 is x naught plus 17.5823. Okay, so we're taking the modulus of everything here. Let's write this more compactly. So this is x naught, okay, plus 35 minus x naught plus 17.5823. Then we take the modulus. So we can now see that x naught will cancel out. So it doesn't matter. So that was what I told you earlier. And x naught does not matter. Whether it was 0 or 5 or whatever, it won't alter our result in any way. So probably that is why the question does not provide it. So even if you assumed it was 0, like it was in A, then you will still get the same results. Okay. So now we have here just minus 35, the modulus of minus 35, that is just 35, okay? Then the modulus of this is just 35 minus 17.5823. So let's bring up our calculator. We have 35 minus 17.5823, 17.5823. So that is going to give us 17.4177. That we know we add 35 to it. So that gives us 52.4177. Okay, so this is what you get now, 17.4177. And then from here, we're going to have D to be equal to 35 plus 17.4177. That's 52.4177. And that gives us 52.4 meters. Okay, so that will be the distance traveled by the body within an interval from 0 seconds to 5 seconds. So that concludes our analysis on this problem. We have the total distance traveled within the interval from 0 to 5. So that is the general approach. We find out the turning point. Anytime you hear total distance traveled, think of turning point. Is there a turning point within the interval of interest? Again, I said in the past that if you're asked to find, for instance, total distance traveled at time t equal to 5 seconds, you already know that starts from 0, okay? If you are going to have any other interval, it will be explicitly stated. But if I told to find as a specific time, that means you have to start from 0 and capture total distance traveled from 0 up to that particular time of interest. Okay, so We have our result right here, and that concludes the analysis of what we have here. So what is really important to note here is the fact that you need to give attention to every detail. You need to give attention to every detail to know if anything has changed. For instance, you might likely just assume that what you have obtained here is what you will need to use here. Now, if this statement was not part of it, if it just says determine the total distance traveled by the pair during the time interval 0 to 5, without this if equals if x dot at 0 equal to this, then you would just use the result you have obtained here for x and v to find out when the what the turning point is, and use that expression for x as well to find the total distance traveled. But that is not the case here, so you must always pay attention to whatever conditions are provided, okay, before you go ahead with the problem statement. So the fact that they are written together or they are connected in some way does not mean that they will have the same equations applied to them, even though it has to do with the same body or the same system. All right, so that is that about that. We'll proceed in the next lesson to consider a different category of problems. Thank you for watching. I'll see you in the next lesson.